Okay, so far we've talked about three assumptions of linear regression. We've talked about constant variance, normality, and independence. An additional important assumption that came up when we were talking about constant variance is the linearity assumption. And so, in addition to those assumptions, we also assume linearity, and this can be checked via a residuals versus fits plot, or by examining the relationship between predictors or a combination of predictors and the outcome. So why does nonlinearity happen? It's often due to model misspecification. And so by that I just mean that you haven't quite specified the model correctly. And so one way to account for this is via the introduction of transformations or terms such as polynomials or splines. And so for the sake of time, we're going to focus on polynomials in this class, but splines are really important and frequently used in linear models. In your reading, I've put an optional section on splines, and I encourage you to at least look this over. In your time here at Wake, you probably will encounter a class that goes through fitting splines and things like that in more detail. So it is really worth kind of having a bit of a sense of. But polynomials are a little bit easier to work with kind of when you're working by hand, and so we're going to focus on that. Okay, so here's an example of a residuals versus fits plot where our linearity assumption is violated. And so what do I mean by that? Well, when we look at this residuals versus fits plot, what are we looking for? We're looking for whether there's any kind of fanning, and so if there's this, if the variance is not constant, or if there's an obvious pattern. And the obvious pattern is what points to nonlinearity being a problem. So as you probably remember from just the last class where you fit a whole bunch of these different residuals versus fits plots under different circumstances, you know what good ones look like, where basically you've got kind of scatter on either side of zero and it looks pretty random. So this is definitely not a good residuals versus fits plot. Okay, so you see this plot, what do? Well, in this particular case, it probably would be appropriate to fit a polynomial. And so a polynomial model is going to be one that just has these higher order terms. So for example, what I've written up here is a polynomial with d degrees. And so instead of just fitting y equals beta 0 plus beta 1x, I'm fitting y equals beta 0 plus beta 1x plus transformations of x, or in this case, x squared plus x cubed, all the way up to x to the d power. So that's what a polynomial is. And you can have these models where, in this case, I just have a single predictor variable x that I'm transforming multiple times to add these polynomial terms to be able to account for nonlinearity. But it's possible to have a model like this where, one of your terms x is calculated using a polynomial, but you have additional predictors, like let's say you have a predictor for age and a predictor for weight, and those predictors are fit kind of in their own way, so they may or may not include polynomial terms. So what that is to say is that just because you include polynomial terms for one predictor doesn't mean you need to include it for all predictors. And so this is an example here where I'm fitting a third degree polynomial. That's what fits this data the best. I know that because I generated the data beneath this, and so I know this is fit with a third degree polynomial. But let's talk about specifically how it's done. So new variables are created. So you leave x is going to be your x1 variable. But then you create an x2, so another variable that's equal to x squared, and a third variable equal to x cubed, and so on for however many degrees of polynomials you're fitting. And so in your design matrix, now instead of having just a column of 1s and x, for example, you're going to have a column of 1s and then a column of x's, and then a column for x squared, and then a column for x cubed, and so on and so forth for each of the degrees of the polynomial that you've decided to fit. And then when you fit this model, you treat this as multiple linear regression where each of these pieces are fit. And so when you do this, it turns out you're not interested in specific individual coefficients. So you're not actually interested in these beta coefficients. In fact, they're pretty meaningless in this context, because if you remember, the way we interpret beta coefficients is it would be something like a 1 unit change in x yields a whatever change in y holding all of their variables constant. But is it possible to hold x squared constant while you're varying x? No, of course not. Those are perfectly dependent. So if you move x up by 1, x squared is necessarily going to also change. And so for that reason, these beta coefficients by themselves are really not interpretable. And we wouldn't try to interpret them. What we actually are interested in are specific, how a specific value of x behaves. So you'd plug in some x value into your function or into your model, and you would see kind of how that value behaves, or what your y hat value or your predicted y value would be for that given x value. And in fact, more often, rather than just doing this for a single x value, what we're actually interested in is the change between two values, so the change between a and b. And so for that, we would calculate the difference between the linear model fit with b plugged into each of the x values, and then subtract that same model with a plugged into each of the x values. And so you get this where we just would be plugging in. So if I plugged in for this equation, if I plugged in b for every x0 here, it's what I've done in these first 4 terms. And then if I plugged in a and subtracted those for every term, that's what these last 4 terms are. And then the reason there's no intercept is because this first part is going to have an intercept. The second part is going to subtract the intercept, and so those just cross out. So we can actually recombine these terms a little bit to make a little bit of an easier kind of formulation of this. And so basically what we're doing is we're multiplying our beta 1 times the change between a and b, plus our beta 2 times the change between b squared and a squared, plus our beta 3 times the change between b cubed and a cubed, plus beta 4 times b to the 4th, a to the 4th. And if we had more polynomial terms, of course, this would just keep going. So you would do this up to the d polynomial terms that you had in your model. So how do you actually pick a and b? Well, sometimes there's a sensible a and b that someone like a stakeholder might be interested in. But if there's no other information, a sensible choice might be the 25th and the 75th percentiles of x. So I've drawn that here on this graph. So for example, if I were to plug those in, I'd be saying a change from the 25th percentile to the 75th percentile of this x variable yields a kind of whatever that slope ends up being change in y. So how do we actually calculate the quantile in R? Well, there's a function in R called quantile. This may have come up earlier in the class, but I just wanted to make sure you knew how to do it so that if you're asked to calculate kind of the change between the quantiles, you know how to calculate those quantiles yourself. So for example, I've just generated some random x variables here, a vector of 100 variables just for demonstration purposes. And the way you calculate that quantile is using the quantile function. So you plug in the vector that you'd like to calculate the quantile for, and then you plug in the quantile you'd like to calculate. So in this case, since I want a 25th percentile, I'm going to put 0.25. And it spits out the quantile here. So negative 0.45 is my quantile, my 25th percentile. And of course, that corresponds to exactly right here where this ended up, negative 0.455. And then for the 75th percentile, the exact same thing. I use the quantile function, except now I change this to 0.75, and that ends up coming out to 0.698. And so that falls exactly right here, 0.698. So you see non-linearity on your residuals versus fits plot, and you want to know how to pick the degree of freedom for the polynomial. Well, this is actually pretty challenging, and the best way to do this is actually via a method called cross-validation. We're not going to get into that in class, but for now I'm going to tell you what degree of polynomial to use. But just so you know, the reason why we need to have more sophisticated methods than kind of what's mentioned in your book is if you use the data that you are observing to try to tell you what degree of polynomial to choose, you're often going to end up overfitting your model. And what I mean by that is it's possible that you can sort of think that you should be fitting this high degree polynomial because you're sort of reducing your error in your data that you're looking at. But if you were to see a new data set, you might not see kind of exactly the same wiggle that you see in your current data set. And so that high degree polynomial might have too many terms in it or might be too fit to the original data set, which would make your model not as useful on a new data set. And most often when we're doing linear modeling, we're trying to fit a model to a specific sample. But we are doing so with the expectation that that generalizes to a larger population. And so I just want to give some sense for that basically when you're trying to kind of determine what types of models to fit, variable selection and thinking about kind of what variables to include are really important questions, but they are challenging questions that require some sophisticated techniques. So cross-validation is really the best way to try to get at this question. For now, I'm going to tell you the degree of polynomial to use. If we have time in this class to talk about variable selection, we'll talk about some of the more sophisticated techniques that you can use. All right, so what I want you to do is I want you to copy the code below to create a design matrix X and an outcome Y. And so this code is basically just going to generate, here I've got, the first part is just a vector of 1s for my design matrix. And then our X term here, our predictor, I've just randomly generated from a normal distribution. So I'm randomly generating 100 values here. So this design matrix as is going to have 100 rows and 2 columns. So just go ahead and copy this code. This is in your application exercise. It's also, you can get the slides on the website. And then I want you to generate this outcome Y that I've written here, so you can copy this directly to get your vector for Y. And so what I want you to do is I want you to add to this design matrix, or to X, so that you can fit a model with a third-degree polynomial. So you're going to be adding columns to X in order to fit that third-degree polynomial. And then I want you to fit this model using linear regression, and so using the formula that we're so familiar with, the X transpose X inverse X transpose Y. And then I want you to calculate the expected change in Y given a change from the 25th percentile to the 75th percentile of X. And so remember that X here, or our main predictor, it's going to be that second column of the design matrix. So that's going to be the value that you're going to be interested in getting the 25th percentile and the 75th percentile from. Of course, your beta coefficients are going to come from that X transpose X inverse X transpose Y. And you're going to basically see, using those beta coefficients, if you can calculate the expected change in Y given the change in X. So go ahead and work on that, and when you're finished, you can upload it to Canvas.